Well, welcome to section 4.4, the definite integral. And this topic will have several videos with it. And the topics we're going to cover is the review of summation notation, the definite integral on the calculator, which you're going to love, the properties of integrals, the definite integral as an area, and the average value of a continuous function. Okay? Before I get started here, I'm going to just open up my Inspire calculator while I'm doing this. And so what we're going to do here is look for instant estimates for the left-hand sum and the right-hand sum. So this is kind of a review from before. So this notation that we have here, it's the integral from 1 to 6 of 3 over x squared dx. And they're telling us that n is 4. So let me explain what everything is here. I'm looking for the area under the curve. This is my a, this is where I'm starting, this is where I'm ending, a to b. This is my function f of x that I'm going to use for a pattern, okay? And this is the change in x, all right? And they tell us n is 4. So this is the number of rectangles or the number of subdivisions, okay, that we're going to have. So they said, why don't you estimate what you think the area under the curve of 3 over x squared is going to be with 4 subdivisions. Okay, now before I even start doing this, I've got to make a table of what's going on. So I know this formula, delta t equals b minus a over n, because this tells us how we're going to do our table. And when I put it in there, I know that delta t is going to equal 6 minus 1 all over 4. So I am counting by 1.25. So that's my change in my x. So let's set up a table here. Okay. And we're going to start out with a 1, because that's what we can start out with. And then we're going to count by 1.25. So there's 2.25. And the next one is 3.50 when I add that. The next one's going to be 4.75. And the next one, and the last one, we're going to end at 6. So this is a little bit longer than I need it to be. We're going to end at 6. Now, this is my beginning here. Now when I plug in the 1, and I'm using this in here, and you can actually put this right in your calculator, 3 over x squared. So when I do that, 3 over 1 squared is 3, and then I put that in there, 2.25, it's going to be 0.5926. If I put 3.5 in there, 0.2449, put 4.75 in there, 0.1330, and 0.0833. So what I have here are really the points that are on my graph at intervals. If you look at it here, I have 1, 2, 3, 4. There's my 4 rectangles, and they're 1.25 apart, so I set it all up. Now when I do the left-hand sum, this is a review. The left-hand sum, you're going to start on the left. We're going to start here, okay, and we're going to stop 1 short. So the left-hand sum is I'm going to take the 1.25, which is the change, and then I'm going to add 3 plus 0.5926 plus, oh, that's a 9, sorry, plus 0.2449 plus 0.1330. And when I do that, I get 4.9631. So that's my left-hand sum. Since this is a decreasing function, this is going to be my upper bound or my upper estimate. My right-hand sum is going to be, this lets me write here, all of a sudden it stopped writing. Here we go, right-hand sum, as I'm going to do 1.25, but now when I do the right-hand sum, I'm going to start here and go to here. So it's going to be 0.5926 plus 0.2449 plus 0.1330 plus 0.0833, and this should be my lower estimate, and it is. It comes out to 1.3173. So if I were going to ask you to tell me an estimate, we would actually average these two, divide it by 2, and come up with an estimate. Now that's with 4 subdivisions. Now let's look at it. Suppose we want to do the left sum for this, but we want to use n to be 50. You're like, wow, n is 50. That means I have 50 subdivisions. Can you imagine? I would have this really long table. This would be quite time consuming if we were to try it by hand. Instead, we have a calculator program that will do this for us. So basically, if you would please, write down all these steps, and then I'm going to do one with you because I've opened up my Inspire here so that we can look at it. So I'm going to have it open here for you to look at. Oh, close. All right, so let's open this up. So when I'm going to do this with you when we get started. All right, so let's go back to this. So let's put these down first. So first of all, you're going to do menu. Okay, you're going to do 6 for statistics. So just copy this down, and then you have something to follow. 3 for list math. And 5 for sum of elements. Okay, now that will put the sum in here. So this will give you the sum. Okay, so this will tell you the sum. And then when we want to do the sequence, okay, because that's what we're doing next, you're going to do menu. And it's going to be 6 for statistics again. 4 for list operations. And then 5 for sequence. Okay. Now I'm going to put this down here, the basic form, all right? So the basic form, if I want to do the left-hand sum, okay? So we're going to do the left-hand sum first. Remember when we do the left-hand sum, we start way over here on the left. So we start right at 1, okay? But we end 1 short. So watch what we're going to do. So your left-hand sum will look like this. Sum, parentheses, sequence, because that's what we're going to do, the sum of this sequence. Then we're going to do f of x. Now we're going to start right at start at f of x, and our term is an x. We're going to start right at a, end 1 short, so it's going to be b minus delta x times, in terms of delta x, times delta x, okay? So let's try that again. Your left-hand sequence, left-hand sum, is sum sequence. Then you're going to put your function in terms of x. This is your beginning point. You're going to end 1 short, so you can say b minus whatever my change in my x is, which is my delta t, times your delta x, in terms of delta x, times delta x, all right? Let's do our right-hand sum. Our right-hand sum is very similar. It's going to look like this. Sum sequence, same function, in terms of x. Now here's where the change is. When you do the right-hand sum, you start 1 over, so it's going to be x plus, a plus delta x, comma, then you're going to end at b all the way to the end, delta x times delta x. So here's the other one. So this is for the right-hand sum. Sum, sequence, your function, x. So here's your changes, going to be right in here. Okay? So now you're like, okay, what does this all mean? So let's look at this function that we just did, and look at the difference between here. When we did this, look how our upper sum and our lower sum are quite a bit apart. And you're like, well, it's not that much. Well, for this function it is, because it's way down at 1.3 or up as high as almost 5. So we want to know exactly what the area is between that. So if I do this, okay, now I want you to look at this. N is 2, 10, and 50. So I'm making more and more subdivisions, making more and more rectangles, if you will. All right? So I'm going to do one of these with you to show you how we get this. And I'm going to do the 50 with you because the 50 should be the best. And as you do this, they get closer and closer. So I'm going to give you what this would be. If I had just 2 subdivisions, this would be 8.1122. And the right-hand sum would be 0.8206. Okay? In this case, when we did this one, your delta t was b minus a all over n, so I was counting by 2.5. All right? When I do 10, this is what came to be my left-hand sum. 3.3482 and 1.8899. Do you see how they're closer together? My delta t in this case would be 6 minus 1 all over 10, which is now I'm counting by 0.5. So it's more frequent, and I have 10 subdivisions, almost 10 rectangles. So this is getting closer and closer together. All right. Now the 50 should be even closer together. So I want to do one of these with you. All right. So first of all, let's just put it in the calculator and then I'll fill this in for you. So bring up your calculator, and if you need to stop this to grab one, please do. So I'm going to start at home, and I'm going to do a new document, and I want a calculator. New document, and I'm going to add a calculator. All right. So let's go through these steps, and we're going to do just like the let me see now. We'll do the left-hand sum. Okay. So first of all, we're going to do menu, just like I said. And then after you hit, you're going to hit 6 for statistics, and then 3 for list math, and then we're going to hit 5 for the sum. So the sum will show up. That was the first part. Then we're going to hit menu again. We're going to do statistics again, and now we want to do the 4 for list operations, and then 5 for sequence. So it says sum of the sequence of numbers. Now, once that's there, let's put in the functions. So I'm going to do control fraction, and it's 3 over x squared. So I'm going to come down and put x squared here. Then I'm going to arrow over and put a comma. The next thing you have to do is put the variable, which is x. Now, if we're going to do the left-hand sum, we're going to start at a, and a is 1, comma, and then we're going to end 1 short. Well, our delta t in this case is 0.1, so we're going to put in there 6 minus 0.1, because that we're going to stop 1 short, comma. Okay, then we're going to do, after that, the 6 minus 0.1, we're going to put in our delta x again, so I'm going to put 0.1. That's the 50 subdivisions has a delta x of 0.1. Then get out of that parentheses, and then we're going to say times, whoops, let's get out of there, let's delete here. Let's move over more and say times 0.1. So when I hit enter, when I have 50 subdivisions, my left-hand sum is 2.6508. So let's go back to our thing here. This is 2.6508. Now, I probably should have showed you before I did that, but your delta t here is 6 minus 1 all over 50, which is, that's where we got the 0.1. That was your delta x. Now, if I did the right-hand sum, I would get this. Oh, let's undo that. Okay, so here we're going to put 2.3591. Do you see how these are getting closer and closer? And that's with 50 subdivisions. So can you imagine if we did 100? If we did 150 and got closer and closer and closer, we'd have the actual area. Well, we have an actual program on your calculator that finds it. So let's look again what we have. So if we want to find the exact value of the area, the exact value, not I want to say an estimate, because before I was estimating and then we would average them. Here is the area under the curve. Okay, so it's the integral from 1 to 6. So here's your AB, here's your function dx. You can actually put that in your calculator this way. So let's put down the keystrokes and then we'll do it together. Menu, then you're going to hit 4 for calculus, then you're going to hit 3 for integral, because that's what that is. It's the integral. We're doing integration. All right. What you're going to get is something like this. It's going to come here. It's going to have a box here, because you need to have put your beginning. This is your A. This is your B. So you're going to have to put where you start to where you end. Then you put your function in here. So this is your function, whatever it is going to be. Okay. And then this is, it's going to say D box, and then normally you're going to put DX. Okay. So let's put this in our calculator. In this case, we're going to have put 1, 6, 3 over x squared dx. So I actually love this calculator because you can put it in exactly how it looks up there and then put equals. So let's bring it up. So here's the calculator. So I'm going to do menu, and we're going to do calculus, and we're going to do, oops, calculus, and then we're going to do our integral, all right? And see how it's got here. So I'm going to put 1 here, come up here, put 6, and then our function is a fraction, so I'm going to put 3, and then here, whoops, 3 is right here. Undo. Let's try this again. Menu, calculus, integral. They've changed this because I put 3 for integral and it's not anymore. 1 up here to 6, and we're going to put a fraction here, Then here we're going to put 3, and x squared's here. Sorry, sometimes it's harder to do it here. Arrow over, and we're going to put an x here. And when I do that, you just hit enter. It tells you the exact area is 2.5. So if you were to look at what we've been doing, you can see how this is getting closer and closer to 2.5, but the actual area is 2.5. So I'm actually going to change this right here because they've upgraded it since I've done this the last time. So it's going to be 2 for numerical integral. Okay? So that's cool. I mean, this gives you an estimate, but this gives you the exact value. Now, let's kind of just do a little bit background, and then I'm done with this video, but I wanted to make sure you had a little bit of background on where it came from. So again, we're doing, all right, delta x here equals b minus a over n on this interval ab. So we've been doing that. So what we did for that is we actually were doing the sum of your function times the change in x, all right, and we were doing whatever n was. But if I put a limit in front of it as n goes to infinity, as you noticed, it gets closer and closer to the actual value. All right. So let's look at how the definite integral came about. If f of x is greater than or equal to 0, then each sum end of the left or right sum is the area of the rectangle. The sum of these areas of these rectangles is an approximation for the area under the curve. So we want to find the exact area under the curve, so they have come up with where we can use an actual integral. So here's your lower limit of integration, here's your upper limit, so this is your beginning, your end. Here's your integral sign. This is your function as an integrand, and x is the variable of integration. Okay? When you find the value of your integral, you have evaluated the integral. So definition, if f of x is greater than 0 for all x in this interval, a is less than x and less than b, then the area between f of x and the x-axis on the interval from x equals a to x equals b is given by this. And the one thing I want you to know is area is always positive. I want you to remember that, okay? Now let's do a little quick history here on the side before we go forward. History, just so you can see where everything's coming from, all right? So I want you to remember delta y over delta x, okay? That's slope, right? We switched that to dy dx, okay? So this was basically slope. We're using the Greek letter here, delta, which means the change. And then we switched for d, because d is Roman, for differential, okay? So this course, we started out with this, and we now went to dy dx. Now what we've been doing is we've been saying, okay, if I take the limit as all my rectangles get to infinity, of the sum of these, I'm going to start when k is 1 to infinity, of f of x delta x, it now changes to this, where it's now elongated. It's an elongated Roman S for sum, because that's what you're doing is sum, and it's smoother like a curve. And here's your beginning, here's your end, here's your function, and then we have dx's. So basically the f of x's have become so crowded together that they're not choppy anymore, and it's a continuous sampling of x values from a to b. So it makes it for the exact area. Now I have this one last picture here I'm going to show you, and I want you to know this because I said area is always positive, and I want you to keep that in mind. So you're going to do the value of any integral, the value of the integral is the area above the x-axis minus the area below the x-axis. So when I do the area of the integral from a to b of f of x dx, it's always the area above the x-axis minus the area below the x-axis. Now you're saying, well, you just said area is always positive. But if I was actually doing this function right here, your integral, when in your calculator, they would count this as positive area, this is negative, this is positive, and this is negative. And the final value is they'd take this area, they'd subtract this little piece, add that area and subtract that and give you a final answer. So if I tell you to find the integral, I don't say anything about area, you can just plunk it in your calculator. Okay? And if you do that, it's going to do this. It's going to take the area above and subtract. Okay? Versus if I want you to find the area enclosed by the function and the x-axis. Okay, so if I ask you just to find the integral, by all means, start at A, end at B, put that here, put your function in, and put dx and get an answer. But if I actually ask you to find the area that's enclosed here, we'll call this area A, this area B, area C, and area D. This is what you're actually going to have to do. You're going to have to do the integral from A to, we'll say whatever this point is going to be here, this number here, of A, okay? And then you're going to have to subtract, because this is actually going to be a negative area from this piece to this piece of B. Then you're going to add the integral from here to here of C, and then you're going to subtract the negative integral of D, so that you would actually, all these would turn out to be positive. This answer will be different here. So let's look at what we put in here. So this is 0. This is -1, -2. So actually, instead of saying A and B, what we're going to do here is actually put numbers in. So here's our area B. So this is 1, 2, 3, 4, 5, 6. So this is -6, and this is 1, 2, 3, -3. This is -1, and this is going to be 2 and 4. So this is what we actually write it in here. So let's actually put numbers in here so you can see how this works. Okay, ready? I would say the integral from -6 to -3 of A, and that would give me a positive area. Then I'm going to subtract this negative area, because this is going to turn negative, so I'm going to go from -3 to -1 and put B in there. And that will give, then that'll make it positive because I subtracted a negative area. Then I'm going to add C, which is from -1 to 2. That is positive. And then I'm going to subtract, because this is going to be a negative area, from 2 to 4. And then this answer will be different than if I asked you just to find the integral. Okay? Now the next video we're going to practice this, but I wanted you to make sure you understood that. That's the end of this video right here.